So if a basis for a single particle state is phi j, indexed by the integer j, then a general state for one particle is given by an arbitrary linear superposition of them. The general state for n identical particles is an arbitrary linear superposition of the tensor product of all those states. Now these coefficients, if they're indeed indistinguishable particles, have lots of redundancies. Anytime I swap any of those two indices, I either have to get exactly the same coefficient if it's a boson, or I have to get a minus sign if it's a fermion. And what that means is the only unique piece of information I need to specify my coefficient is the number of each kind of index. So we could write our state using the C-bar notation. Although that looks very similar, it's actually a major shift in notation. We're just doing a generalization of what we did up here for two particles and two states, but we're doing it for an arbitrary number of states and n particles. Here we had for fermions a state that had exactly one particle in state A and one particle in state B. And so that would have looked like number of A was 1 and number of B was 1, which we'd probably write something like this. 1, 1. This state down here was the bosonic version of that. So this is 1, 1 for bosons, and it's actually a different state under the hood than it is for fermions. But all we needed to know about this state was how many particles were in each single particle state. Now it's really important to realize that in this notation, this was the state of the first particle, and this was the state of the second particle. But in number notation, we're deliberately getting rid of any idea of which particle is which, as we should for indistinguishable particles. So this slot here tells us how many particles are in state A, and this one tells us how many are in B, and they have nothing to do with which particles are which. We can, of course, relate the states in number notation here to the old original states. For bosons, the number state is equal to some normalization factor times every possible combination of states in our original notation that can give us the right number of particles in state A and state B and state C and so on. So a trivial example would be one particle in state A and no other particles. And that would of course just be one particle in state A. Another example would be the example we had above, where we had one particle in state A and one particle in state B and no others. And that would just be, or we might have two particles in state A. Or we might have one particle in state A, one particle in state B, and one particle in state C. So you can see that this normalization constant is simply there so that these states are by definition normalized. And the normalization constant depends on exactly how many particles you have in each single particle state. So what we've gained from this occupation number notation is that we've built in the symmetry or antisymmetry of the bosonic or fermionic states, respectively, into the notation itself. So when you write things down in this notation, you can't write down an illegal state. It has to have the right symmetry or antisymmetry. And that means that every physical state can be written in this notation, and every state that you write in this notation is a physical state. And so it's the obvious choice of notation for dealing with many-body quantum mechanics.